Of course, we won't always be asked to um, make confidence intervals or even perform hypothesis tests longhand with, having to do all the calculations. A lot of times, say like on the final exam, for example, everything will be given to you in an output like this, and you just have to read it. So this was a real-life study that by the Pew Internet and American Life Project. It tracks the behaviors of Americans on the internet. In 2007, they published a report that describes some of the behaviors of American teenagers in online social networks, such as Facebook. Teenagers who had online profiles were asked, "We'd like to know if your last name is posted to your profile or not." And the confidence interval outputs for the two computer programs are below. StatCrunch is here, Minitab is here, and Group 1 was boys and Group 2 was girls. So here we go. Now, how many boys were surveyed? Well, boys were group 1, so we have to look here for total 1. That's 500 in StatCrunch, or N is 500 right here in Minitab. How many put their name on Facebook? That was 200, because you can see right there, X is 200, or up here, the count is 200. What is P1 hat? So that would be the proportion for boys. That's 200 over 500, which is 0.4. Now, Minitab very kindly just gives it to you, 0.4. By the way, that's not a 1 at the end there. That's a cursor mark from that. And then StatCrunch does not give it to you, so you'd have to find it yourself with a calculator or something like that. 200 over 500. Now, what is the confidence interval? That's the 0.1529 to 0.2631. It's right here. Let me insert a shape right here. There we go. So you can see it right there in Minitab. 95% CI, that's confidence interval. And then up in StatCrunch, it's even easier to spot. There's the lower limit and there's the upper limit. Right there. Okie dokie, so there's our confidence interval. Now, does this confidence interval suggest that there's a significant difference between boys and girls? Okay, well, if there wasn't a difference between them, if the proportions for the boys and girls were the same, then when you take the difference, they'd be 0, right? Because if boys are 40% and girls are around 40%, when you subtract 40% minus 40%, it's 0. Now, we don't expect it to be perfect, like what if boys were 40% and girls were 38%? I mean, that's really close, right? So we make a wiggle room for it, i.e. that's what you're doing when you make this confidence interval. You're making that kind of give or take that you expect. But 0 isn't even in this interval. This interval goes from 15% to 26%. 0 is nowhere close to it, which means there is a significant difference, right? Because 0 is not in the interval, there appears to be a significant difference between the proportion of boys and the proportion of girls who are willing to put their names up on Facebook, which shouldn't be any great shock to anybody. You can imagine there might be a lot of reasons why that might be the case. But you can tell that there's a significant difference because 0 is not in there. If it had gone from negative 0.15 to positive 0.26, that would be a different story. But since these are both positive numbers and 0 is not contained within, there's a significant difference. All right, now what do you do if it's dependent samples? What do you do when it's all part and parcel of the same group, which is what we're going to do here. This is called the Mcnamara's test for two proportions. It has very specific rules. Oh, that's a typo. Observations. Sorry about that. Where the outcomes differ, etc., and it has to have these followed. So it has to be dependent samples, which is kind of weird. We haven't really worked with that very much. The total of observations has to be greater than or equal to 10. That is the observations in the two disparate groups, which is F12, which is always up here, and F21, which is always down here. And the 1, 1, 1, 2 thing is just labeling, like this is row 1, column 1, row 1, column 2, row 2, column 1, row 2, column 2. That's all that the 2, 2, 2, 1 thing means. We are always doing a two-tailed test for these. It's never anything else. So it's P1 equals P2, P1 not equal to P2. That's it. That's all you get. You don't get the other ones. Alpha is just like before. And then the test statistic is this weird thing. Those vertical lines there are absolute value. So absolute value. And then we have a classical approach or p-value approach, which we'll see hopefully as we do this. and then we have to make a decision. Now, the weird thing about this is that even though it's a two-tailed test, we're only ever interested in the right tail, because the absolute value thing makes this thing turn positive every time, no matter what. So there is technically another tail over there on the left, just like over on this one over here. But the issue is that it won't ever matter, because it's always going to be positive no matter what. So you'll only ever be looking at the right-hand end of it. All right, so let's do this. We have a recent general social survey. Asked subjects whether they believed in heaven or whether they believe in hell. For the 1120 subjects who responded, the table below shows the table, the data in contingency table form. Contingency tables. Remember, we learned about those in chapter 4, long time ago. All right, so the rows are the response categories for belief in heaven. The columns are the belief in hell and the U.S. population. In the U.S. adult population. Let P1 denote the proportion of people who believe in heaven, and P2 be the proportion of people who believe in hell. All right, so explain why this is dependent sampling. Oh, where should I begin? All right. There we go. So the same people are being asked to answer 2 questions. So their response to one obviously is dependent upon their response to the other. In other words, remember, dependent means that you have one group of people that's being asked twice, right? They're being asked about heaven and hell. Now we're supposed to determine, is there a significant difference between P1 and P2? Use the classical method. All right, so I'm just going to give you a little hint here. The classical method's how you're going to have to do this for doing it straight up by yourself. I have computer programs that can get me the results in a computer output, but it's not something you're going to be able to do. StatCrunch doesn't even do this one. So you're stuck doing this longhand with Excel, your calculator, whatever. There's very little to do with Excel, but we can work it. Okay, so let's see here. Let me type this up. I'll be right back. All right, so step 1, we want to know if there's a significant difference. So P1 equal to P2, P1 not equal to P2. And again, these will always be two-tailed for this particular type of test. Alpha was 0.05. Then we have this lovely test statistic right here, which I just found with a calculator or Excel. I mean, whatever. Use Excel as a glorified calculator. You need to find 125, take away 2, because what you're really interested in is this top right cell and this bottom left cell. Why? Well, if you're trying to show that there's a difference between believing in heaven and hell, the people that believe in both and the people who believe in neither kind of don't interest you, right? So this isn't going to show you that they're different. You're assuming that they're the same. So if you assume the null hypothesis that the proportions are the same, then what difference does it make to you about the belief and the not belief? What really shows that whether they're different or not is this top right corner here. The people that believe in heaven, but they do not believe in hell. And down here, 2 people believe in hell, but don't believe in heaven. Okay? So that's where you're going to be seeing whether or not these 2 proportions are really different from each other, right? The belief in heaven and hell is really a question of, are there a lot of people that believe in one but not the other, and vice versa? Okay. So you found 125, take away 2, and then that's 123. You take the absolute value of it, which in this case it's positive anyway, and then you subtract 1. So that gets you 122 for the numerator. The denominator is the square root of 125 plus 2, which is the square root of 127. And just grab a calculator and divide that, and you'll get about 10.8, which, just for the record, I mean, at this point in our lives, hopefully you're at the point where you go, 10.8, that's a lot of standard deviations. Yes, it is. Because this is a z-score, that's a lot. Now, don't forget, chi-squares are always floating around. That's not big for chi-square, because chi-square is squared, so everything's positive, and you get into the 30s and stuff. But for z and t, 10.8 is really, really huge, way off screen. So, for example, I drew this lovely picture, and this is what you draw by hand. I know I put both tails on there because, well, that's just how I am. But technically, only the right one needs to be bothered with, because we'll take that absolute value, it'll turn positive. 10.8 is so far off this curve, it's kind of ridiculous. It's way over here on the right-hand side. So you are totally going to reject, right? Reject that null hypothesis. Z0, which is 10.8, is greater than Z alpha over 2, which is 1.96. Now, this is not a test that your computer's, StatCrunch does not do this test. Calculators do not do this test. There are programs that do it, like Minitab down here, but it's not going to be one you're going to be able to do That way I could give you a computer output and have you read it, but that's about it for the p-value method because you don't really know. If you really wanted to find the p-value on your own, what you'd have to do is use norm dist, right? You know the value is 10.8, and you'd find the area in the tail, and then you'd find the area in the other tail, and you multiply by 2. But this one's going to be so close to 0, it's not worth bothering about. All right. So there is sufficient evidence to support the claim that there's a significant difference in the proportion of people who believe in heaven and hell. And you can kind of see it in the table. There are a lot of people who believe in heaven but not hell. And then there are very few people that believe in hell but not heaven. And there's a significant change going on here. Right? So there's a whole bunch of people that really want to believe in heaven but not believe in hell so much. Right? Convenient for them, don't you think? I believe in heaven, so that way I know I'm going to a good place, but not necessarily hell. So, all right. We're done with Fisher's test. Let's finish this up for for sample size. So we learned, and it's on the inferential statistics cheat sheet, so you don't have to memorize this, but down here, up here, right here, 2 proportion ones. So how can you figure out how many people you need to go poll, right? Well, you could use this formula if you have a previous estimate. So like, for example, the recent presidential campaign, they had last week's polls, so they would put in last week's number for Obama here for proportion 1 and Romney here for proportion 2, and they'd be able to figure stuff out. But if you're doing your first poll of the season, you'd use this one over here, 0.5, because you don't know what it is. You don't have a clue. All right, so let's go back here. Suppose a medical researcher wants to know if there's a significant difference in heart attack rates between those who take a placebo each day and those who take aspirin. What sample size should be obtained if she wishes to be within 3 percentage points with 95% confidence? Assuming, for part A, that she had some kind of old study that had already been done on this topic, and she had some previous estimates for the proportions. And then part B, she doesn't have a previous estimate. So we pretend like we don't have this prior study. All right, let me type this up. Hold on one sec. All right, so I typed it up. So it's just glorified typing into a calculator, to be honest. So you take in the 0.017 times the 1 minus 0.017, that's this one. And then you take the 0.009 times 1 minus 0.009. Then you add them up. You just do all this with a calculator. And then you find 1.96 over be careful. It's 0.03. Catch that. You got to change 3 percentage points. See that right there? You got to change it to 0.03 because it's got to be in a decimal form. And then you square that. So you got to find this whole bit first, get that number because of order of operations. Then you do the parentheses, take 1.96 over 0.03, then exponents, square that, right? And then you can multiply. So find the bracket part first, find this part next, and then multiply them, and then round up no matter what. Because you can't pull 0.7 of a person. It's against the law. So round up no matter what to the next number. Because you can't go any lower. If you go any lower, you won't have the confidence you wanted. Oh, and the 1.96 came from the grand old, it's 95% thing again. 95%, remember, 95% confidence, that's 1.96. Okay, so what about if you don't have a prior estimate? Then it's the same kind of deal, but you don't have that whole front bracket rigmarole. You just have 0.5. So you do 1.96 over the error, 0.03, and then you square it. You got to square it first because of order of operations. Exponents comes first. So do that parentheses, 1.96 over 0.03, square it, and multiply by 0.5. That'll get you 2134.2. And again, you can't pull 0.2 of a person, so you're going to have to make it 2135. Now notice that this is in each group. So you've got, 112 in the placebo, 112 in aspirin, 2,135 in placebo, 2,135 in aspirin. And did you notice how much smaller it is when you have prior estimates? If you've got previous data, it makes it so much simpler to get the size sample you need. When you have no clue what's going on and no idea what's going to happen, that's when you've got the bigger numbers. And in medical studies, that can be really expensive. So what they'll often do is have something called like a pilot study. They'll study, just a couple hundred people first, get some prior estimates, right? And then they'll go do a big study from there if they show promising results. All right, we are done with 11.1. It's all finished. I'll meet you back here for 11.2. More hypothesis testing and confidence intervals. I know it's a shocker, but that's what we'll be doing. See you then.